Well, thank you. And at first I would like to thank, of course, the organizers and the ICTS for making this event possible and for inviting me to present this lecture series. And on the other hand, I also would like to welcome you to my very first lecture here and, of course, the very first lecture of this program. I'm sure we'll have a great time. So, I also thought it might be a good idea to actually introduce myself to you and tell you a little bit about my background, because I don't really know a lot of people here. So academically, I was raised in Braunschweig, which is one of the 4 international GAP centers. I'm sure Alexander will say a little bit more about GAP. So I started quite early doing computational group theory / algebra, and my PhD thesis, in fact, was on finite P groups, so P groups of maximal class. When I finished my PhD, I took up my first postdoc position in Auckland, where I continued doing research in computational group theory. I also started to use the computer algebra system MAGMA. And afterwards, I went to Italy. But again, I worked with GAP and did some computational algebra. And now since 2013, I'm at Monash University as a senior lecturer in Australia. I should emphasize, I'm not in this 90 million building here in the front. I'm in this very old building at the end. So this is where mathematicians live, right? We don't need anything more. So this is my background. I started quite early in my career doing computational group theory, and I have some experience with GAP and MAGMA, which is great because the title of my lecture series is Computing with Finite P Groups. This is what I'll be talking about. And before I start, let me say a few organizational things. Firstly, whenever I speak about P or P group, P is of course a prime. And when I talk about groups or sets, in most cases, it will be a finite group and a finite set. So I won't recall this assumption on all of my slides, so keep this in mind. Talking about my slides, my lecture material, so my slides, tutorials, and tutorial solutions maybe, will be uploaded at this website address here. I will upload everything after my lecture because, frankly speaking, it's the first time I'm giving this lecture series. It's the first time I'm using these slides. It might be that there are a couple of glitches or things I have to change before I upload my material. So this will happen after each lecture. And one last comment is about the assumed knowledge, which is a bit tricky because I wasn't quite sure what I can assume and what I can't assume. So of course I assume we all know a little bit of group theory. And in particular in the very first lecture today, where I basically introduce weighted polycyclic presentations, it might be that you have seen some of these things before. So apologies if you're bored. And if you haven't seen this before and you need more input, please approach me maybe after the lecture or in the tutorials. We can talk about it. All right, so this is housekeeping. So now let's start. Why are we actually interested in P groups? Well, I think a very good answer is by just looking at the number of groups which exist. So this is a table which in its left column says group orders, and in its right columns have the number of isomorphism types of these groups. And if you look at this table carefully, then some numbers stick out. For example, you see here that at group order 8, we have suddenly 5 groups, whereas before we only had 1 or 2 groups. Suddenly at order 16, we have 14 groups, and then this goes on. The next big jump here is at group order 32, where we have 51 groups, and so on. And finally, 64, we have 267 groups, right? And why are these numbers special? Well, they all are powers of 2 or 3 times the power of 2. And so they are closely related to P groups. And in fact, this is not just by accident. It is basically known that there are many P groups around. If you fix the order P to the n, then the number of isomorphism types of these groups is well, P to the 2n cubed asymptotic. So we come back to this later. This is really just the initial motivation, really saying that there are many P groups around. And in fact, there is this folklore conjecture saying that almost all groups are P groups, in the sense that if you fix the group order and you count all groups up to that order and you check how many of these groups are P groups, then most of them will be P groups. For example, 99% of all groups of ordered mouse 2000 are 2 groups. So there are many P groups around, which is the first reason why P groups might be of interest. And of course, we all know that by the Zulu theorems, every finite group, non-trivial group, has P groups as subgroups. So they are really around. What else? Well, you know the class of nilpotent groups, finite, as I said before, they are, of course, direct products of P groups. The class of solvable groups, well, they are iterated extensions of P groups. And to some extent, one could say that the theory of P groups is kind of a counterpart to the theory of finite simple groups. You know, finite simple groups are the building blocks of all finite groups. And if you choose the simplest building block, you get the cyclic group of prime order. And if you just restrict attention to this simple building block, you get all P groups. But even there, the theory is kind of really intricate and complicated. So there are many challenges related to P groups, for example, classify P groups, so not even the precise number is known. And there are also many reductions to P groups. So for example, this famous restricted Burnside problem, there are restrictions of certain statements in cohomology. There are P-local subgroups which are important in the context of finite simple groups. So P groups show up more or less all over in group theory. So they are really important and exist in abundance. So they're fascinating, and the good news is they are accessible to computer investigations. So this is why we talk about this topic in this lecture series. We do that. So this is what I plan to speak about in the next 5 days. We already had the motivation, so I hope you're all motivated that we want to study these objects. Today's lecture is basically about PC presentations, certain weighted polycyclic presentations we use to represent P groups. Then the main core of this unit is centered around these famous algorithms here, P-quotient algorithm and P-group generation. So this will take second and third lecture together with the classification by order part here. Then we talk a bit about isomorphisms and automorphisms of P-groups, and in the very end, I hope to showcase an example where we use all these computational techniques to derive some new theoretical results. So this is a rough plan. The main resources, as you can also find on my uploaded sheet, are basically the paper of Eamon O'Brien about P-group generation. And for some general informations, I would refer you to the Handbook of Computational Group Theory, which also contains many useful descriptions. So you don't have to copy this right now. It's also uploaded on my literature sheet. Okay, so let's start. Let's talk about PC presentations. You know, it's about computing with groups. We somehow have to tell the computer how we want to work with groups. And there are different ways of describing a group in a computer. For example, take the dihedral group of order 8. We can represent this group simply as a permutation group. We have a 4-cycle, and the transposition generates the 8, which is great. One way of describing this group. We can also let this group act on a linear structure, vector spaces, which means we describe our group in terms of matrices, which often is also a nice way of describing it. Or lastly, we can simply choose a presentation. You know, we have a finite set of generators, and we have basically a list of rules or relations which these generators satisfy. So these are 3 descriptions of exactly the same group, and somehow we have to decide, okay, which of these representations will be used to work with P groups on a computer. And as you might know, for P groups, it's quite a good idea to use presentations, special types of presentations, polycyclic presentations. So let's talk about that. We have to go back a little bit to really make sure that we're all on the same page. So I decided to recall some basic things about group presentations. It all starts with a free group and an abstract generating set. So F is a free group on an abstract generating set X. And then we have a set curly R here, which is just a set of words in the generators and their inverses. These will be the relations. Take the normal closure of these words, call it capital R. With a normal subgroup, we can build the quotient. And then this group here is called the group defined by the presentation with generating set X and basically relators curly R. And we also write it in the following way using these angle brackets, saying X bar R is that group defined by the corresponding presentation. And and informally, as you know, it is really the largest group, which is generated by X, which has generators satisfying these relations we have imposed. So here's one example, which we've seen before, this dihedral group of order 8, generated by 2 elements, R for rotation, M for mirror. the relations we have imposed were that r to the 4 is 1, m to the 2 is 1, and then this commutator relation here. Although I have to be careful here, there are two different terms. It's once you can call a thing a relator, which means it's really just a word in the generators and its inverses. Or sometimes it's more convenient to rephrase this relator and write it as an equation. So this relator here is really the same as saying r conjugate by m equals r to the 3. This is called a relation. So what can we do with this kind of representation? Well, we can deduce some properties this group has. For example, this relation r to the m is r cubed simply tells us that when we have rm, we can move m to the left of r by raising r to the 3. So it tells us how to interchange r and m. Which means when we have some arbitrary word in r and m, we can use this rule to put all of the m's to the left. So every element can be written using this rule in this form that m is on the left and then we have some power of r. And taking into account that r to the 4 and m squared is 0, we can reduce these exponents. Right? So there are at most 8 elements in this group, and they look like that. Yeah? Now, on the other hand, we know that the dihedral group of order 8 has 2 generators which exactly satisfy these relations. So we deduce that this group G is in fact isomorphic to the group G8. Yeah? So this is one way how we can analyze the structure of a finitely presented group. Okay. Of course, there are problems attached to that, and there's serious problems. So in general, when you have a group defined by a presentation, it is proved that it's algorithmically undecidable to answer even the most simplest question. So in general, you won't be able to decide whether this group is finite, trivial, or abelian. And it's all basically based or related to the word problem, which says if you have an arbitrary word in your generators, there is no algorithm which always tells you whether this word is trivial. It's a really bad situation in general, because it tells you can't almost do anything. Right? However, group presentations still are very important. Right? So they are firstly a very compact way of describing groups, and they also arise in several areas of mathematics naturally, like in algebraic topology as fundamental groups, for example. And it's not all lost, because there exist efficient algorithms which allow you to do something. Yeah? There are so-called quotients algorithms, which we will discuss a little bit later. There's coset enumeration, which sometimes can help you to do something. And there exists really a vast amount of literature dealing with this problem, what you can do in a finitely presented group. And the last point here is really important. In fact, many classes of groups can be studied by group presentations, and P groups is one of these classes, which we can really use finite presentations. So we have to find a good way of finding a presentation for our P. And for this, we have to recall a little bit of background knowledge. So you probably know that if you have a P group, non-trivial, then its center is also non-trivial. Yeah? I hope you remember all that. And this is the basis, basically, for constructing the upper central series. If you have a non-trivial P group, you know its center is non-trivial, and then what you do is, well, you factor out this center, you get a quotient group, which is again a P group, and you take its center and lift it back. And you iterate this, and what you get eventually is a strictly increasing series of normal subgroups. It's a central series. Closely related to that is the lower central series, where you start at the top of the group, and you iteratively take these kind of commutators. And it turns out, again, you will get a strictly decreasing subgroup series. You will terminate in the trivial subgroup. All sections are central, and in fact, the length of the series here is the same. There's always a question why you start with different indices, but this is how it's done in certain books. It always confuses me as well. One has to take care of what index you start. Yeah? And the length of the series is called the nilpotency class of G. Okay. So here's one example. Take the dihedral group of order 16, generated by well, a rotation, which is order 8 cycle, and then this transposition here. So element of order 2. its lower central series looks like that. Well, it has length 3. And the sections of the series, well, the first section, if you quotient out the very first term here, you get an elementary abelian subgroup of order 4, and all the other sections are cyclic of order 2. Now, as I said, all these sections are central, which means the group acts trivially on them, which means whenever you have a section which is not already cyclic, well, you can refine this section so that you get cyclic sections. So what could we do here? Well, the first quotient here is elementary abelian of size 4. We could simply introduce an intermediate normal subgroup, which makes it into a refined chief series. So simply add the normal subgroup generated by R, then we have a series where all sections are now cyclic of order 2. And this can be done really for every P group. When you have your P group and your lower central series, for example, you can refine this series so that you really have always cyclic sections. Each subgroup here is normal, and you have cyclic sections. Really good structural result about P groups. And this basically proves that G is called polycyclic, made up from many cyclic sections. In fact, this is also the definition of a polycyclic group more generally. Group is called polycyclic if you have such a polycyclic series, so a subgroup chain in general, where each term is normal in its precessor, and the quotients are all cyclic. Yeah? Polycyclic group. Here's yet another example. It's not a P group, it's the alternating group of rank 4, where it's generated by a 3-cycle and it's double transposition. If you look at the polycyclic series I've defined here, we have the first term, which is line 4 group, elementary abelian of size 4. It has index 3 in the bigger group, and then we have a normal subgroup of index 2, and then the trivial subgroup. Now, the good news about polycyclic series is, well, each quotient is cyclic, so generated by a single element. So what we can do in this situation is, we simply take an element Gi, which lies in Gi, but not in Gi plus 1, which generates this cyclic factor. We can simply do that. We have our cyclic series, we choose these elements, and these elements, it's called a cyclic sequence, will be really important in later applications. So in this particular case, we could choose, for example, G1 to be a 3-cycle here, because it lies in the bigger group, but not in the line 4 group, and then we have these double transpositions. So we can choose this simply by the structure of having these cyclic quotients. And such a ordered set of elements is called polycyclic sequence. Yeah? Polycyclic sequence. And now each element Gi generates the quotient Gi modulo Gi plus 1. This quotient has some order, call it Ri. And then we say that the relative order of this element is Ri. So we have our elements Gi up to Dn, and the relative orders are Ri up to Rn, where again Ri is defined by the order of the corresponding cyclic quotient. So from this definition, it's kind of clear that the group order of these terms of the cyclic polycyclic sequence is exactly the product of these relative orders. So it's a very useful thing to have. If you have these polycyclic sequence and the relative orders, you can immediately define the terms of your polycyclic series, and you also know the orders of these groups, simply the product of the relative orders. Okay, so here's one example illustrating that. We have again the dihedral group of order 16 with our 2 generators R and M. One polycyclic sequence is simply, well, take M and R. Yeah, the corresponding sequence is, well, the whole group, the normal subgroup generated by R, and the identity. And it's easy to see that these quotients are indeed cyclic. Cyclic of order 2 and 8. So this polycyclic sequence has relative orders 2 and 8. Now, polycyclic sequences are not unique by no means. We could have also chosen M, R to the 4. You get a different polycyclic sequence here. And if you look at the orders of the quotients, you now get order 2, order 4, and order 2. So the length is different, and we have different relative orders. Also, other things can happen. So here we have M, R cubed, R square. it again will define a series, and the funny thing here is one of the relative orders is 1, because given this set, two of these groups in the sequence will actually coincide. So this can also happen. Yeah? All right. So why are these polycyclic sequences useful? Well, this is probably one of the main applications. If you have such a polycyclic sequence, n, G1 up to Gn, then it happens that you can write every element in your group in the form G1 up to some power, up to Gn up to some power. So it's an ordered word, G1 up to Gn, and all these exponents here are between 0 and the relative order -1. Yeah? This is a very useful thing to have, this normal form. Yeah. Let's just do the proof. It's actually very, very simple. Let's use induction. You know, if we only have one generator, well, then our group is cyclic, right? Our group is cyclic, and of course, every element in that group can be written uniquely as the generator to some power. So that's easy. So now let's consider the case that we have more than one generator, and we have been given some element G. Remember, if we consider the first quotient G modulo G2, it's a cyclic group generated by G1, the coset of G1. So the element G times G2, this coset, lies in that group. It's a cyclic group, so we know we can write it as some power of the generator of the cyclic group. So there exists a unique E1, which satisfies this equation. Unique E1. So we already have fixed E1, and it lies in the right range. So what do we do next? Well, look at this equation of these two cosets. Multiply by G1 to the minus E1, and what we get is an element G dash, which now lies in G2. Yeah? And now the good news is, if we truncate our polycyclic sequence and get rid of the first generator, then we have a polycyclic sequence for G2. And now we can use induction. So simply by induction, we know that this element G dash has this normal form, exactly in the form we want it to be. But now you see, we are interested in the normal form of G, so what remains to do? Well, we have to put this Gi to the minus Ei onto the other side. We just multiply by it. And then we are done. So it's a very simple inductive proof, which shows this really powerful result that every element in a polycyclic group, given with this polycyclic sequence, has this normal form. Okay. So here's one example which illustrates that. Again, we have alternating group of rank 4. Let's take this polycyclic sequence here. It has relative orders 3, 2, and 2. Let's take this element 1, 2, 4 in G. So how would we proceed? Well, we consider this element modulo the first term of the sequence. This here, it's G1 to the power 2. Then we multiply by G1 square inverse to get this element G dash, which now lies in G2, and we can compute this element. It's 1, 4, 2, 3. And now we just continue with this setup here. G dash can be written as G3 can be written as G2 times G3. So we get G double dash, which is now an element lying in G3. Looks like that, and then we are basically done. So we've iterated this construction, which was illustrated in the proof, and we really found our normal form. So it's a very easy. Okay, so as I said, we want to somehow describe P groups by finite presentation. So now we want to use this knowledge that every P group is a polycyclic group and has this polycyclic sequence to construct a presentation, a group presentation describing this group. So what do? Well, we take our group G with polycyclic generating set X and relative orders R of X, and we want to get a group presentation out of it. So we want to see first what kind of relations these generators here satisfy. So the first thing to observe is take one of these elements, gi, and consider its power to the ri. Well, you know that gi modulo gi plus 1 has order ri, so when you consider this power, you know that gi to the ri lies in gi plus 1. Yeah? So we know by the previous lemma that we can write this element as a normal form, but it starts at gi plus 1, not as 1. Yeah? So we basically start with one index further up. Yeah? This is called a power relation, because we consider powers of generators to the relative order. Now, what about conjugation? If j is less than I, then we know that ji lies in dj plus 1, which is normal in gj. Yeah, so gj normalizes this, which means that this conjugate here can be written, in this form. We have again a normal form, and it starts at gj plus 1. So it's a conjugate relation. And now let's take these relations and build a representation out of them. So we mimic these relations we've just seen. So we take a new abstract group. It has n generators, the same as we have generators here. Yes? Gn. Oh, it's Gj. So it's a conjugate. So we conjugate the element Gi by the element Gj. Yeah? All right, so we take a new abstract group, the same number of generators, and the relations are exactly these guys here, but written in X. So we make it more abstract. It's a formal definition now. So we really take the same exponents we've determined here to make up new words in the free group, basically on x1 up to xn. Well, you can do that, of course. And it gives you a group, well, because it's a finite presentation. But the statement of this result here is that this group is, in fact, isomorphic to the group you started with. Yeah? And it's also a polycyclic group, and the generators x1 up to xn are a polycyclic generating set, and the relative orders are exactly the same relative orders. So this is the statement of this result. And how to prove it? Again, it's remarkably easy. Simply define a map from the new group here, H, to the old group by mapping xi to gi. Yeah? The images, g1 up to gn, they satisfy all the relations we've made up here. But it's not a surprise, because we have made up these relations exactly by mimicking the relations we have seen. But now that we have this, it's Van Dyck's theorem, which tells us this map is an epimorphism. It's a surjective group homomorphism. Right? But now by construction, it's easy to see that this group here is polycyclic, and it has order at most G, but we have a group epimorphism onto a group which has order of G. So this epimorphism is an isomorphism, and we are done. So if you have a polycyclic group, and you observe these power relations and conjugacy relations, you can really make this into an abstract group presentation, and well, you have your presentation describing the group. So this is starting from the group, getting this presentation. Here's one simple example again, alternating group of rank 4, generating set G1 up to G3. You simply observe these power relations and conjugacy relations, and you write all this in a group presentation. Here it is. So this is a polycyclic presentation describing the alternating group of rank 4. So every polycyclic generating set determines a unique polycyclic presentation, and in particular, every polycyclic group can be defined by such a presentation. Okay. So now more generally, you can also directly write down a presentation and call it polycyclic. You don't have to start with the polycyclic group by default. And that's basically what's written down here. So again, we have n generators, and the only relations we have are relations of the type we had seen before. We have power relations and conjugacy relations. Now these exponents here, these numbers, S1 up to Sn, I don't call them relative orders. I call them power exponents, because this is the power we consider in the relation. we will see that sometimes they might not be equal to the relative orders we see. So this is the general definition of having a polycyclic presentation. And here's one convention which is often useful. Many of these commutators can be trivial. If two elements commute, then this relation doesn't really say anything other than these elements commute. So in a polycyclic presentation, you often omit these relations. So everything like xi to the xj equals xi, you usually don't write down. But now you don't want to be confused, so what you do is you write PC in front of it to indicate, aha, it's a polycyclic presentation. If two elements don't have any commutators given, then you assume they commute. Okay. So now theorem, if you have such a presentation with power exponents S1 up to Sn, then first off, it's a polycyclic group, and the generating set is a polycyclic generating set. Basically really follows from these relations. And similar to the lemma we had before, every element in the group can be written in a normal form, in this form, where all these exponents here are in the range 0 up to Si minus 1. So power exponent minus 1. But we have to be careful. From these relations, we can only read off that xi gi to the Si equals 1. This is what we can read off this equation, but this only implies that the actual order of this element divides Si. It's not necessarily equal Si. So the relative orders of this generating set, which I denote by R1 up to Rn, are in general not equal to these power relations if you start with a general polycyclic presentation. They are divisors of these guys. When you start with a polycyclic group, as we've done on the previous slide, then it's all fine. But if you just write down a polycyclic presentation, things can be a bit different. Okay, so here's one example of where things are a bit different. It's a group defined by 3 generators, and it's a polycyclic presentation, as you can see here. Polycyclic generating set x1, x2, x3. And the power exponents, well, look at the powers. We have 3, 2, and 5. So the power exponents are 3, 2, and 5. I show you that the relative orders are 3, 2, 1, which essentially means the third generator here, x3, is the identity in that group. And the group in particular has order 6 and not 30. So how can we see that? So it's basically an ad hoc computation here now. The first thing to observe is that x2 to the power 10, well, x2 to the power 2 is x3. So if we power it to the power 10, then this is x3 to the power 5. So look, x3 to the power 5 is 1. So x2 to the power 10 is 1. And we deduce that the order of x2 must be a divisor of 10. Good. Now secondly, what happens when we conjugate x2 with x1? Well, look at your presentation. x2 to the x1 is x2, x3. This one. Now x3 is x2 squared, right? So we can write x2, x3 as x2 cubed. Now when we conjugate, when we take x2 to the power 9, well, it simply means we take x2 and conjugate it by x1 3 times. Each time we raise the power by 3, so x2 to the power 9 is x2 conjugate with x1 cubed. Now x1 cubed is x3, and x3 is x2 squared, and these guys commute. So what have we seen here? x2 equals x2 to the 9, so the order of x2 divides 8. So we have the order of x2 divides 8, and it divides 10. So 5 for sure doesn't divide the order of x2. But if 5 doesn't divide the order of x2, then x3 must be trivial in the group G. As I said, it's an ad hoc computation, but you can use such things to really verify that things are not as they seem to be, right? So you would have guessed that x3 has order 5, maybe, but it hasn't. It's actually trivial. It's the identity. And also it shows us that with respect to power exponents, normal forms are not unique. So the identity can be written as, well, all generators to the power 0, but we can also write it as all generators but the last one to the power 0 and the last one to the power 1. So normal forms are not unique in this situation, which is usually considered to be a bad situation because you want normal forms to be unique. So if things like that happen, then you call the presentation inconsistent. If normal forms are not unique with respect to power exponents. And if the normal form is unique, then you call it consistent. And in fact, it will turn out that a polycyclic presentation is consistent if and only if its power relations, if its power exponents equal the relative orders. So here they don't equal, as we see. Relative orders are 3 to 1, power exponents are 3 to 5. So if these two things are different, then it's always inconsistent. So we want to have a consistent presentation for our P groups. And well, there is an algorithm which allows us to check consistency, so you don't have to do these ad hoc arguments, which can be tedious and often probably don't work. There is an algorithm, and to discuss this, we have to talk about collection and then consistency checks. So this is what I want to do next. So what is collection? Well, you know, if we have a polycyclic presentation, then we have normal forms, basically, with respect to these power exponents. Now let's take a reduced word, which is just a word in the generators. And by reduced, I simply mean that adjacent generators have different subscripts. Yeah? And we can also assume that all these powers here are positive integers, just to avoid some technicalities. If you have something negative, you can replace this element by its inverse, and then you can rewrite it. Okay, so this is now about collection. Take such a word, and we call it collected. Well, if it's in the normal form with respect to S. So it's basically just giving it a different name. So what does it mean to be in normal form? Well, first of all, it means that the indices here are increasing. So we have I1 is less than blah, 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 up to IR. Normal forms always have increasing labels of the generator. Secondly, all these exponents come from the prescribed range. They all lie between 0 and the power exponent minus 1. But this is the normal form, just the definition. So basically being collected is just being the normal form. So if your element is not collected, well, it's not a normal form. So there must be some situation in your word which violates the fact that you are collected. So what could happen? Well, it could happen, for example, that you have a subword which looks like this. You have x, ij, and x, ij plus 1. And ij is greater than ij plus 1. For example, take the word x3 cubed times x1. It's not collected because x1 is right of x3. So you would have expected it to be left of x3. This is one situation. Or it could be that you find a subword where the exponent hits exactly the power exponent. You want all exponents to be in the range between 0 and power exponent minus 1. If you hit something like that, then it's also something which tells you, the word is not collected. So these are minimal non-normal subwords, non-collected subwords. And now collection is a method which takes any word and transfers it into an equivalent collected word. So how does it work? We take a word as before, and the algorithm is as simple as that. You simply do the following. You choose one minimal non-normal subword, and you look up your relations and replace this minimal non-normal subword by something which is collected. For example, if you have a minimal normal subword like that where you hit the power exponent, well, then you look into your relation, you find that this guy equals something in the other generators, and you simply replace this occurrence. And similarly for this situation where there is a smaller generator right of a bigger generator, you know how to commute two of these generators by the rules in your relations. So you simply replace this obstacle here by something which looks a bit better. You can do that, and well, it's not by no means clear that when you do this that you will always terminate, but it's a theorem saying that if you do that, you will actually always terminate and you get a collected word. So basically, you just look at your word, you point to the places where it's not collected, and you rectify the situation. You just do this until you're done. The proof is actually, it's not too difficult. It's again by induction, basically. So, but I skip the details here for time. It's in the handbook, so if you're interested in it, maybe have a look at it. So this is what a collection algorithm is about. And of course, there is one technical thing. There's a choice involved. If you look at your word and you have several places where there are minimal non-collected subwords, well, you have to choose where you start. And there are some collection algorithms which prescribe a certain way you choose these subwords. Yeah? So these are three of them. The first one is called collection to the left. Basically doing what it says here. You first look at all occurrences of x1. If it's collected, you know x1 must be the leftmost element. So if there is some x1 hidden in the middle of the word, you choose the rightmost one and move it to the left. And once you've done it, you continue with x2. So you collect everything to the left. Secondly, you could collect from the right. So here you start looking at the right of your word and choose the first minimal non-normal subword and rectify that. And you simply continue that. Or you collect from the left. So here you start on the left, you look for the first minimal normal subword from the left, you correct it, and then you continue. In practice, collection from the left seems to be most efficient. There exist actually papers on that which support this claim. So this seems to be the thing which is used in practice. Here's one example. I want to demonstrate these three collection principles. Again, it's a dihedral group of order 16, the presentation we've seen before. And we want to collect the word x3, x2, x1. It's not normal because, well, the ordering is wrong. Now, all the relative orders here are 2, so instead of writing x something, I simply write down the label of the element. Right? So 3 to 1 means x3, x2, x1. So now we want to collect to the left. So we first look at x1 here, and it's next to a 2, which is not in the right order. So we want to rectify that. We have to know how do x1 and x2 commute. Look up in your relations here. They commute by adding an additional x3 to the right. So we commute this and get 3, 1, 2, 3. Now if we collect to the left, we look again at the first occurrence of x1, which is not all right. It's this one here. It's next to a 3. So how can we rectify that? Well, look in your relations. x3 and x1 commute, but we have to add x4. So we get 1, 3, 4, 2, 3. So 1 is now leftmost, which is good. The next generator we have to deal with is x2, and you see there is an x2 here, which is not in normal form. It's next to a 4. So how do 4 and 2 commute? Well, luckily they do commute, right? It's 1, 3, 2, 4, 3. So I hope you get the idea now. You just look for all these non-normal subwords, you collect, and you get the element x1, x2. So this is to the left. What about from the right? So here we look at the first non-normal subword starting from the right. And again, we start actually by the same subword because this is the first subword which is not in order. So it's the same here. And again, the first step is the same, it's still the same. But here's something different. Right? On the left side, you know, we look at the first occurrence of x2, which is not in order, which is the underlined pair 3, 2. If we use from the right, then we look at the first non-normal subword, which is, well, from the right, and this is 4, 3. So here's actually a different choice of normal subword, non-normal subword. We correct that, and we get 1, 2 again, which we would actually expect, right? Because the presentation is consistent, we should get the same word. And here's from the left, so here we start by looking at the first non-normal word from the left, 3, 2. We just do the same thing as before, but in this case we actually have 2 steps less, and again we get the element x1, x2. So this is just to illustrate that there are different ways of collecting your elements. Okay. So this really tells us how we can get a normal form, right? If you have a polycyclic presentation, and you have some word in the generators, you can use the collection algorithm to get a normal form which equals to the original element. Good. Now the main question we want to answer is at this stage, well, if I give you some polycyclic presentation and we observe these power exponents here, is this presentation consistent or not? In other words, is the list of power exponents the list of relative orders or not? What do we have to check? Well, we have to check essentially that every element in the group has a unique normal form, which is by default an incredible task you don't want to do. But luckily there is a reduction. You don't have to consider all words in the group. You only have to check a certain number of test words. So let's maybe look at the first element here. So it's basically the group element xk times xj times xi. Right? In a group, and this is where we work in a group, these two elements are the same, right? It's just a law of associativity we apply here. We bracket different. So these two elements must be the same. So what we do now is we collect these words, but we collect them a bit differently. We start with the expression in brackets first. So we look at this element. Xj, xy is non-normal because j is bigger than I. So we collect this subword, and then we continue collecting the whole thing. And eventually we get some normal form. And now we do the same with the right word here, but we start with xk, xj. And we get some normal form. Yeah? If these two normal forms are not the same, then the presentation is not consistent. If they are the same, we continue with all the other test words. So really note that in the group, all these elements you see left and right must be the same. Yeah? They are the same group elements. For example, here we basically have x here, and here we have xj to the power sj plus 1. But it's the same element which is written here. So in the group, these two elements must be the same. What we check is whether the normal forms we obtain by collecting them differently coincide. So here's one example. Presentation you see here, and we check the second condition here for j equals 1 and I equals 2. So we have to take x2 to the power s2, which is the power exponent you see here, 2. And we collect the word in brackets first. So what is x2 to the power 2? Well, it's x3, right? It's still not a normal form because x3 is left of x1. So how can we commute x1 and x3? Well, luckily they commute, right? There's no rule which tells us otherwise. And this is a normal form, x1, x3. And now we do the same thing with the other word we have to check. So this is now x2 times x1, but we start by collecting the term in bracket first. So we have to rectify x2, x1. We have to change these two elements. How do they commute? Well, look in your presentation. They commute, but we have to add an x3. So we get x2, x1, x2, x3. So here we have to collect again. We get x1, x2 square, x3 square, and now we substitute x2 square, x3, and we get this expression. And now we have a normal form. Generators are in order, and the exponents are less than the power relations we have. Now the thing is, are the two normal forms the same? Well, they're not. Right? Here we have x1, x3. Here we have x1, x3 cubed. So we deduce this presentation is not consistent. And in fact, we know that in the group, these two elements must be the same. If they are the same, we deduce that x3 must in fact be the identity. So x3 here doesn't have order 5, it has order 1. All right. Good. So far, what have we done? Well, we have seen that every P group has a polycyclic, can be represented by a polycyclic presentation. We have seen how to check whether a polycyclic presentation is consistent. We can collect words, etc. Now, for most algorithms we will discuss in the next lectures, we will need a kind of special polycyclic presentation. It's called a weighted power-commutator. So there we have some further rules we want to have satisfied by our. So this is the definition. It's again a polycyclic presentation. We have generators x1 up to n. We have some relations. The two main changes are, first change is every relative order is p. You can always achieve that, but this is what we want to have for weighted power commutator. And the other thing is often relations, conjugate relations, are written as commutators, and in such a form that the subgroup generated by GI are in fact normal in the group. Remember, in a polycyclic group in general, you only have that GI is normal in GI minus 1. Using this kind of presentation, you have the GI. Oh, okay. There's one other minor thing. You know, we also. So every other generator must be the right side of one of these relations. We soon see an example. And this relation is then called the definition. So this is really a technical thing which is used internally in some algorithms. Don't worry too much about it. And I'm not commenting on the weight here. I'll make a brief comment in the next lecture. So here's one example, which is a weighted power commutator presentation. So you see we have these commutators here. Every relative order is 2. And a minimal generating set is x1, x2. So the group is rank 2. So the other generators, x3, 4, and 5, must be the right side of one relation. So let's see that this is the case. Okay, x3 is here the right side, and it's also here the right side of a relation. So now we can basically choose which of these guys we define as being the definition. So for example, it doesn't really matter. take the commutator here to be the definition. Oh, yeah, ignore the comments on the weights. Decided to talk about that in the next section. So what about x4? Well, x4 is here. It's here. It's the right-hand side of one relation as well. It's uniquely defined. So this is the definition. And x5, well, several choices, so you can choose which one you take. But it's, again, the right-hand side of one of the relations. One example. So why are polycyclic presentations or weighted polycyclic presentations useful? So let me wrap up this lecture. But first of all, they are useful because they really allow us to solve the word problem. You know, in a general finitely presented group, you can't do anything. But here we have normal forms. We can solve the word problem. You simply collect, get your normal form, and you can compare words. There is additional structure, of course, if you have a weighted presentation. And this is used in some algorithms. For example, you can do consistency checks more efficiently. You can reduce the number of test words if you make use of the fact that you have a weighted polycyclic. And lastly, which is quite important, every weighted polycyclic presentation gives us a normal series. Every group is normal in the big group. And many algorithms work along this series. So if you want to solve a problem for G, then the philosophy is, okay, first solve it in the quotient G modulo GK, and then lift it to a problem for G over GK plus 1. So eventually you solve it for G over Gn, but this is G. So many algorithms proceed along this series. And so how can we compute weighted polycyclic presentations? Well, this is something we discuss in the next lecture, and it's related to this famous p-quotient algorithm. So we will discuss this algorithm in detail. So just to wrap up what we've done today, well, we've defined polycyclic groups, sequences, and series. We have introduced polycyclic generating sets, PCGS, relative orders. We had polycyclic presentations, power exponents, and consistency. And it's important to remember that these power exponents are by default not equal the relative orders. We have to check whether the presentation is consistent. We talked about collection and normal forms, consistency checks, and lastly, we have defined this weighted polycyclic presentation. But tomorrow we continue with that and discuss how to compute such a presentation. I think I stop now. Thank you for your attention. This was 1 hour, right? You set this for 1 hour or for 50? Okay, I was confused whether it was 50 minutes.